so excited to introduce to you David DeSanto and Sam Kerr, both with GitLab's product team, to share details of how GitLab is leveraging our latest security acquisitions of Peach and Fuzz. When we shared our strategy with analysts, one even commented that GitLab is going to be a game changer in application security. So see how we're automating this technology within the CI workflow to find vulnerabilities and other types of software flaws that other scanners won't find.
Welcome to Getting Fuzzy, blurring the lines between traditional QA and security testing. My name is David DeSanto. I'm the Director of Product for our security stages, Secure and Defend.
Hi there, I'm Sam Kerr. I'm a Principal Product Manager here at GitLab focused on fuzz testing. And what we're going to be talking to you about today are a few different things. We're first going to start off talking about what is fuzz testing, really cover why you would want to use it. We'll talk a little bit more about some specific types and details about fuzz testing. We'll wrap up and talk about how you can use fuzz testing as part of your own projects. And all throughout the presentation, we're going to have demos to really make it so you're not just listening to us and looking at slides, but you can actually see fuzz testing in the real world. And before we talk about fuzz testing, one of the things we wanted to point out, and this is a universal truth probably most people know, all software has bugs, all software has security vulnerabilities inside of it, no matter what. Because everyone knows about this, a mature software development process involves testing. Testing is very important so that you can find bugs, so that you can find security vulnerabilities inside your applications before you're pushed to production where they might affect your users, your customers, or a hacker or a bad person might take advantage of them. But no matter what you do, testing can only go so far. There's always going to be things that can potentially get through your testing and reach your end customers. We have a lot of different types of testing techniques like system testing, unit testing, and many different types of security scanning, but these don't catch every issue that might be in your program. And this is where fuzz testing can come in, because fuzz testing is designed to catch things that other approaches won't. The definition of fuzz testing really is about giving your application random inputs, sometimes thousands or even millions, to find edge cases that might cause your application to crash or perform in some way that you're not planning on, and that could possibly be exploited by an attacker. Now, I know that sounds complicated, but our goal with this presentation is to make it simple enough that you're excited to try fuzz testing on your own. We really believe at GitLab everyone can commit, and that extends to fuzz testing as well. So let's go through a quick conceptual demo of what fuzz testing might look like. Let's say that you're writing an application that takes a single input, a JSON document, processes in some way, and outputs a report about the customer that was inside that document. So as an example, you might take a request for a balance for customer number 5 and use an authentication token to prove that it's customer number 5. Because you did thorough testing, let's say that a fuzzer were to randomly add the request AAA. Your app would see that it's a bug and an invalid input and send invalid request type as its output. Similarly, if you ask for an invalid customer, your app might notice that and say, hey, this is an invalid customer ID. But let's say that your app didn't test the case where a valid customer ID was given, but an invalid authentication token was found. In this case, the app might give the customer report to the other user. And this is a major security issue that fuzz testing can find. This sort of edge case where one user can use their authentication token to access the data of another user is a major issue, and one that we hope that fuzz testing will be able to help you find your own apps. And so now David's going to talk a little bit more about the different types of fuzz testing.
Thank you, Sam. And now you might be thinking, what do I do now? How do I make this work? I want to break things too. And next we're going to go over how fuzzing works and what are the common types of fuzz testing. So when we talk about fuzz algorithms, this is how the engine creates the test cases that Sam was talking about. The first type is called mutation-based fuzzing. And what mutation does is it takes the input blindly and just starts modifying it. This is commonly referred to as dumb fuzzing because it doesn't understand the structure the application is expecting. Two common ways this occurs. At the top, bit flipping, you can see our input is test data to fuzz. And then on the right, after it's been bit flipped, it's something that I can't pronounce, but it's definitely not the same thing. On the bottom, the other option that's commonly done with mutation is appending data. So again, if you start with the original payload of test data to fuzz, and now you start appending data to it, it is no longer the same thing. It might cause an issue, but you don't know whether or not that's actually even a structure that's valid that the application would even process. The second type of algorithm is generation-based. And this is where the fuzz engine understands the structure and the way to communicate with the application. This is commonly referred to as smart fuzzing because it understands the behavior. So if you're looking at the diagram on the left, this is a state model for something like a REST API. And in here, it shows that the client knows it has to send a request first. It knows what type of request to send. If it's not a valid one, it gets a certain type of code. If it gets a different type of code, it knows it sent the response properly and got the right response. And so it's commonly referred to as smart because it truly understands the workflow of that app. And now let's talk about the two ways that you can do fuzz testing. The first is coverage guided, and the second is behavioral. For coverage guided fuzzing, it has visibility into your source code. And this allows the fuzzer to have contextual knowledge about the application. So because it understands the application, it can provide things such as root cause analysis and point to the line of code that caused the problem, or even just the function. And because it sees the source code and it's interacting with your application at that level, you can do this very early into your application development, even as soon as there's just a couple of lines within your application. Here's an example of coverage-guided fuzzing. You can see here it's a very small project, only has a couple of lines of code in it, but the app might not run yet. You can still fuzz test it. Here in the app, you can see within our function parse complex, there's two if statements. The first if statement is checking the length of the data that's being passed to it and seeing whether it's a length of 6. The second if inside there is actually looking at the data and it's parsing 7 locations. This is a common first-time developer mistake. And within this, you can see that we're actually requesting data that's outside the range of the application. This could be used by an attacker to potentially take remote control of your application if these sort of bugs aren't fixed. And these are sort of things that are not found with traditional testing, but fuzz testing can help you find them. The next type is behavioral fuzz testing. And in this case, the fuzz engine understands the application and understands the expected behaviors. This includes the type of correct response that you receive, as well as what the different error codes it can expect. Because of this, it can fully understand the behavior of the application. And you can help the fuzz engine understand this by providing specifications of the application. And an example would be an open API v3 spec for your REST API. The difference here is that behavioral fuzzing runs against the application when it's running. And because of that, it's now not having access to your source code, but can monitor for those unknown behaviors. Even though it's running against the live application, it can still instrument and help you find the root cause as well. On the screen here is an example of what behavioral fuzz testing would look like. In the top left corner, we have OpenAPI v2 configuration. From that, we can extrapolate out what a known request to the API should look like, and that's in the bottom left corner. From there, the fuzz engine can begin to modify the values. In this case, it's going to apply generation-based approach for an algorithm and mutate the value of the user ID. From there, it can send that request and then monitor for the response. And the response is there in the bottom right. And here what occurred is that the application did not respond with an unknown type. It actually threw an error. And through that input and that expected output, the attacker could begin to look at, or you as the conscious tester for your company, understand that you could potentially do something like a SQL injection based off of this error. So fuzz testing does not replace your existing testing. It actually augments it and helps you test deeper and wider. So if we're looking at the top left box, those are going to be security tools that you use today that find known vulnerabilities that have access to your source code. And by known, what we're referring to is that they tell you if you are violating the OAuth's top 10, you have a CVID issue, vulnerabilities that are known and are defined in the industry. But if you then look to the right, in the top right box, it's now looking at unknown vulnerabilities. These are vulnerabilities known to just your application. They're unique to you. Like that example from the coverage guided fuzz test. If we now go to the bottom left, we're looking at, again, tools like web vulnerability scanners that can find known vulnerabilities in your application. But then again, to the right of that, in the unknown area, things like API fuzzing, protocol fuzzing, they're helping you find unique vulnerabilities inside your application that, again, are very unique to you. And here's a great real-world example of that. Coverage-guided fuzz testing in action. Arctic Engine is an open source game engine that's written in C++. We rolled out at GitLab coverage-guided fuzzing only a couple of days before this customer reached out to us excited about it. They were able to use our C++ coverage-guided fuzzing and found issues that have actually been in the application for a while. They were able to discover these issues that their traditional QA and their security testing wasn't finding. And you can see that in the screenshot to the right. Again, on the screen there on the bottom left is actually the customer responding to Sam, who's our co-presenter here, about how excited they were that they found this and how excited they were that GitLab was able to support them as an open source community, helping them be more secure. And the one example I want to give to you that I think is very exciting, they actually found something with their Wave audio processor. So what was very interesting that they experienced is that the Fuzz engine generated a 2-hour-long audio file that had 1 sample per second. When that was decompressed by their engine, it became 48 gigabytes in memory. That's not something a normal QA tester would do, and not a traditional security tester or security testing tool would do. But with fuzz testing, they found these types of issues with their application, and we're very excited for them that they're able to make a better solution for the open source community. And with that, I'm going to hand it back to Sam, who's going to talk about fuzz testing outside of security, as well as go through a demo.
Yeah, thanks, David. Because throughout this presentation, we've really focused on the security use case that fuzz testing can enable. But you might be asking yourself, is fuzz testing just for security people? And the answer to that is no. One way that you can think about any sort of security vulnerability in your application is it's a normal type of secure software bug that is just exploitable. That said, there are lots of other types of bugs in your application that could possibly be found by fuzz testing, but aren't necessarily exploitable. In this way, you can find both regular traditional sorts of bugs as well as security vulnerabilities with fuzz testing. If you want to get started with fuzz testing in your own projects, there are a number of different ways to do so. There are a lot of great open source projects out there, such as American Fuzzy Lop, libfuzzer, and BooFuzz. These are all freely available. You can try them on your own applications. At GitLab, we host several of these open source projects, and we also host several of our own proprietary fuzzing projects. Now, since we've looked through a bunch of slides, I'd like to stop sharing this deck and let's go through a demo of what fuzzing a real application inside of GitLab would look like. So on the screen now, I'm looking at a repository of a very basic C++ application that just contains a single function. It's called testString. And what this function is doing, it takes a string of input from the user on the command line. It takes the length of that string as a parameter as well. And then it compares that string against this flag, fuzzing is important. If the two match, the function will return -1, and then that'll be returned to the end user. But there's a very subtle bug in this implementation that I've highlighted right here with this str in CMP function. What this is doing, it's comparing the length of the user's input against the flag to see if they match, but it's going to only be ensuring that the length of the flag is involved in the calculation, in the comparison. It doesn't look at all at the length that the user's input is. So let's see what kind of bugs we can find related to that with fuzzing. Now, using that function, if we want to fuzz it, we're going to do a few steps. The first thing we'll do is create what's called a fuzz test harness. This is how we tell the fuzzer, here's how you run my application as part of testing it. This is a very straightforward test harness. all we're doing is we're taking one piece of data. This is how the fuzz engine mutates the various inputs that it's giving to our app for testing. It tells us how long that mutated data is. And we're just going to pass that directly to that test string function that I was showing you previously. Just directly passing the data in as a string and then the length to that function. Once we've written that test harness, we'll go back and we'll look at our GitLab CI YAML file. This is how GitLab defines how jobs in a GitLab pipeline are run and how we'll tell GitLab to run the fuzz testing job. To do that, all we have to do is include a coverage fuzzing template file to pull in all the dependencies and all the other metadata that is going to be about the fuzz testing. And then we tell the pipeline to build this job my fuzz target and build that fuzz harness that we were looking at previously. This is pretty straightforward for a CMake project. You can see this line here, but this also would work with other sorts of build systems like GNU Make or what have you. Then we're doing a single call to GitLab cov fuzz and running the fuzz tester. That's all we do. That's all you need to do to run fuzz testing. So I ran this pipeline earlier today. So if we go look at the results, we can see that our my fuzz target job ran. We can see that it's orange, which means that it found something. Let's take a look at what it found. If we go to our security tab, we can see that it found a heap buffer overflow error. All of this output is coming directly from the fuzz tester, and you can scroll through and see the stack trace. And if we go down to about the middle, we can find the string that caused our application to crash. If you notice, here's our fuzzing is important string. It's the fuzzer actually generated this completely random looking string here. So fuzzing is important, but also put this parentheses and a bunch of L's to crash our application. This is incredibly valuable to see because this is a sort of test case that was automatically generated by the fuzz engine. You saw we did not have to manually write any of these test cases, and assembling it was as simple as pointing the fuzz tester to the inputs of our function, and it was automatically able to find these sorts of crashes. Because this is directly inside of GitLab, we could then start a discussion on it, bring in our security team, development team. We could create an issue on it, or do whatever else we would want to do to actually resolve the issue. And so that's an incredibly quick tour of what fuzz testing inside of GitLab would look like. So to sum up, fuzz testing is incredibly valuable to your apps because it's going to find vulnerabilities, it's going to find bugs in your application that traditional QA and other security tools won't. We hope that by going through this presentation with David and I today, you've gotten excited about fuzz testing, you understand a little bit more about what it is, and you're hopefully going to be trying it in your own applications. Again, GitLab hosts several open source fuzz testers. We encourage you to check out additional resources we have, such as our product direction page, where we talk more about how we view fuzz testing, the problems we want to solve with it, our product documentation to show you more detail about what I walked through in our demo, and also take a look at our upcoming release pages. We've got a lot coming in the fuzz testing space, and we would love to have you use it, give us feedback, and start finding bugs and vulnerabilities in your applications. And with that, thank you very much for your time. Our furry friends really appreciate it, and we hope you have a great rest of your commit. Thanks.